Alright, chapter 10. So now we're going to talk about our sequences. So, this is the start of a very important chapter. So, this is like another very important topic that we're going to look at in Calc 2. And you'll see what I mean going forward, but when we're looking at sequences, and then eventually we're going to start looking at series as well. Well, first of all, we have to define what a sequence is. And then going forward, we're going to start looking at series, which basically is just a sum of a sequence. So let's get started. So note. A sequence is, to put it very plainly, is a list of numbers finite or infinite. It could be finite or infinite. However, most of what we're going to be doing is going to deal with infinite sequences, and later on in the chapter, infinite series. Do not confuse sequences with series, and I'm going to mention that quite a lot in this chapter. But a sequence basically is a list of numbers, finite or infinite, and we're going to primarily deal with infinite of both types. Here are some sequences. So, there's literally infinite types of examples. For example, if I have to sequence 7, next term is 11, next term is 15, next term is 19, and so on. So this seems like a random pattern, and actually there is a relationship between 7 and 11 and 11 and 15 and so on. There's a relationship between each term in this sequence, and basically what it is the explicit formula for this sequence is 3 plus 4 times n, comma, dot, 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 where n is greater than or equal to 1. So this is just an example of all different types of sequences you'll see. And if you think about it, right, this right here is the term when n equals 1. Right? If you plug 1 in here, what do you get? 3 plus 4 times 1, which is 7. That's easy. Right here's the next one. N equals 2. Right? 2 times 4 is 8, plus 3 is 11. This is n equals 3. And so on. Right? 15 plus 3, or I'm sorry, 12 plus 3 is 15. So, that's just, we could express it with an exact expression in terms of n. Here's another sequence. 1, 2, 4, 8, 16, dot, dot, dot. So this one seems to be a little more familiar. This is actually a power of 2. So this is 2 to the nth power, comma, dot, 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 where n is greater than or equal to 0. So, if you think about it, this is the term when n equals 0. What's 2 to the 0 power? 1. What's 2 to the... This is the term when n equals 1. That's 2 to the first power. This is n equals 2. This is n equals 3, and so on, right? And so each term in this sequence is dictated by the value of n in the explicit formula. Okay, these are some sequences, and you could literally, take that as much as you want, but that's the basic idea. Now, I do want to classify these types of sequences. So this sequence right here, because I'm adding terms together, so I'm adding a number to another term. This sequence is called an arithmetic sequence. Why is it called an arithmetic sequence? Because you get an arithmetic sequence you get this by adding a constant to the previous term. So in this case, I added 3 to that previous term. This sequence, so this one's called arithmetic. This one, and this is the one we're primarily going to look at in this course. This one is called a geometric sequence. And geometric sequences, and you're going to hear that term a lot in this chapter, geometric. You get those by multiplying the previous term by a constant. All right. So in this case, well, this is just a power of 2, so I'm really just multiplying this by, each one here, I'm just multiplying by 2, right? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16, and so on. So those are the different kinds of sequences you'll see, but we're primarily going to look at geometric sequences in Calc 2. But there are other, there are other types. There are other types that show up. So, let me make a note here. Note, the expressions (3 plus 4n) and 2 to the n give the general terms of the sequences. And the ranges for n are given as n is greater than or equal to 1 in the first sequence, and n is greater than or equal to 0 in the second sequence. So those two, the indexes of the sequence, of the ranges for the index, and that's what n is usually called. It's called the index of the sequence. That's given to you. That's explicitly defined. Or it's known to start at some, this is basically the starting value of the sequence. So this starts at 1, this starts at 0, because it's told, right? It tells you that's what it is. So, like I'm saying here, the expressions 3 plus 4n and 2 to the n, they give the general terms of the sequences. And you could just write these sequences by giving their general terms. I mean, you don't have to list them out term by term, but what we often do is represent these general terms of the sequence with a dummy variable. So we could just write these out. You could write these sequences by just their general terms. For example, this is the first sequence. I'm going to let it equal a sub n, which is 3 plus 4n, for n is greater than or equal to 1. That's one sequence. And then another sequence I could do is b sub n equals 2 to the n, for n is greater than or equal to 0. So the fact that the fact that I'm using A and B here is not very important. Those are just the names. That's just the particular name of the sequence. They're just dummy variables. So A and B here are they're basically just dumb. They're just placeholders, really. However, the subscript n is important. The subscript n is important. N is the subscript. Of the terms. And A and B are just the dummy variables. N keeps track of the number of terms in a given sequence. So, for example, if I wanted to write out all the terms of this if I wanted to write out a few terms for this sequence, like I did up here, I could just say, all right, starting at 1, a sub 1 is equal to what? When I plug 1 in here, I get 7. A sub 2, that's going to be the second term of the sequence. So, if I were to go down here, so a sub 1, well, plug 1 in here. So that's 3 plus 4 times 1, which is 7. A sub 2, that means this is the second term in the sequence. So you plug 2 in here. And 4 times 2 is 8, plus 3 is 11. And so on, right? This is the most common way we deal with sequences. We represent it with a expression. But you could also write it out term by term, but as you'll see going forward, this is very tedious. This is the best way to do it. The fact that this is A or B is really irrelevant. I mean, this could be any this could be any letter. This could be C of n, D of n, it could be X of n, whatever. Generally, I use A and B, but they're just dummy variables. Alright, so that's the basic structure of how we define a sequence. Alright, it's just a list of numbers. So how do we plot a sequence? Like, how do we actually plot a sequence? How to plot a sequence. So it's really, just like you would plot anything. You're just plotting ordered pairs on a graph, right? So what if I plotted letter B here? So if I plot the sequence B sub n equals 2 to the n for n greater than or equal to 0. So I'm just going to draw a basic coordinate axis like I usually do. Now the horizontal axis is going to represent the value of n, and the vertical axis is going to represent the actual term of the sequence. Like in this case for letter A, it was A sub n, A sub 1, A sub 2, and so on. So in this case, it'll be, the vertical axis will be B sub n. So, all right, well, we already did it up here, right? I already listed the first few terms of this. So I'll just do it over here for completion, but n sub 0. So when n is 0, right, what's the first term of the sequence? Just plug 0 in here. 2 to the 0 is what? Is 1. All right. I'm sorry, this isn't n sub 0. This is b sub 0. My bad. B sub 1. That's the next term. Plug 1 in here. You get 2 to the first, which is 2. B sub 2. Plug in 2 here. You get 4. And so on. 8. 16. And I could keep going, but I just want to plot a first few terms of this sequence. So this is when n is 0. So this represents the ordered pair 0, 1. This represents the ordered pair 1, 2, 2, 4, and so on. And you can see by that, it behaves like an exponential curve, and that makes sense because 2 to the nth power is an exponential function. So it behaves, if I were to plot these ordered pairs on here, they start off relatively small. So here's 0, 1, here's 1, 2, 2, 4, 3, 8, 4, 16, and you can see as it keeps going on, like this, the first coordinate just goes in increments of 1, but the second coordinate starts getting bigger and bigger really quickly. So this is exponential. So when it comes to plotting a sequence, it's really not much different than plotting a function. As a matter of fact, they're practically they have the same inherent properties, and you'll see what I mean when we deal with like actual sequences. Basically, what we do when we start looking at series is we could treat the terms of a sequence like its own continuous function. So yeah, all right. I do want to make an important note here before I go on to some, I do want to make an important note here that I'll finish off down here at the bottom. I could squeeze it in here. So note, the order of the numbers in a sequence is important. What do I mean by that? So, for example, if I had the sequence 0, 1, 0, 0, 0, dot, 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 and this sequence 1, 0, 0, 0, 0, dot, 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 even though they contain the same type of terms, they're in a different order. So these are two unique sequences. The ordering matters. So these are different sequences. These are different. Just keep that in, just keep that in mind. The ordering of the terms is important. Okay. So let's look at an example here on the next page. Write the first 5 terms of the sequence b sub n equals 5 minus 2n, where n is greater than or equal to 0. So this is a 5. It just looks really ugly. And this is a 5 as well. My 5s always look ugly. You know that by now. So, that's very easy. That's as easy as I think it is. So, write the first 5 terms of the sequence. So, again, you don't have to write this out every time you do it. You don't have to write, a sub 1, a sub 2. You could just list the terms 7, 11, and so on. But it doesn't really matter. It just as long as it's clearly defined how you want to do it. So, you know, if I want to be consistent here, so b sub 0, so plug in 0 in here. That's easy. 5 minus 2 times 0, which is 5. B sub 1, plug in 1, so 5 minus 2 times 1, so that's what? 5 minus 2, right? Because 2 times 1 is 2, so that's going to be 3. B sub 2, so that's going to be 5 minus 4, which is 1. B sub 3, so this is the first term, second, third, fourth, and then because we want 5 terms. So when I plug in 3 here, getting 5 minus 6, which is negative 1. B sub 4, so 1, 2, 3, 4, 5. And then 5 minus 2 times 4, which is 5 minus 8, which is negative 3. And that's it. That's a pretty easy one. What about this example? So, same instructions, right? The first 5 terms of the sequence a sub n equals 5 times negative 1/3 to the nth power, where n is greater than or equal to 0. Alright, so this looks a little different. By the way, what kind of sequence was this? This was an arithmetic sequence. What kind of sequence is this? I'm multiplying 5, so this is geometric. Alright, so this one, you know, a little trickier, but not, you know, not too difficult. A sub 0. So plug in 0 here. So you got 5 times negative 1/3 to the 0 power. Well, anything to the 0 power is what? Anything to the 0 power. So, you know, you could use your calculator, but you should know that. So negative 1/3 to the 0 power is 1. So I have 1 times 5, which is 5. Okay. So the next term, so when a sub 1, so you plug in 1 here, so negative 1/3 of the first power, well, that's just going to be negative 1/3 times 5, which is negative 5/3. A sub 2, so negative 1/3 squared is going to be what? It's going to be negative times the next, that's going to be 1/9 times 5, which is 5/9. A sub 3, so this is cubed, so I'm going to have a negative still there. So I'm going to have 3 to the 3rd power, which is 27, and 1 to the 3rd is 1, so I'm going to have negative 5 over 27. And finally, a sub 4. Well, this is going to be to an even power, so this will be positive. 1 to the 4th is 4, or 1, I mean, and 3 to the 4th is 81. So I'll have 5 times 1 over 81. So those are the terms of the sequence. And, you know, like I said earlier, you could just list these terms out. You don't have to write the actual dummy variable. You could just write the terms. Like in this one, you could write this as 5, comma 3, comma 1, comma negative 1, comma negative 3, dot, dot, dot. I do want you to note that you should always write dot, 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 because these are just the first 5 terms of a sequence, but this sequence keeps on going. So for this one, you know, 5, comma, negative 5/3, comma, 5/9, comma, negative 5 over 27, comma, 5 over 81, comma, dot, dot, dot. You know, you could just write it this way, but there's certainly nothing wrong with writing it this way or this way. Okay. All right. So, listing the terms of a sequence, that's pretty straightforward. All right, but what we're often, so the thing that we're usually interested in with a sequence is what does it go to? Like, what value does it trend towards? Like, does it trend towards a specific value? So if I kept going with the sequence, what's it going to go to? If I kept listing terms here, well, you would see that eventually I'm just going to get to negative infinity. Because I'm going to get bigger negatively, right? Here, this fraction keeps getting bigger and bigger, right? The numerator is always going to be 5. Now maybe negative 5 or positive 5, but the denominator is going to get bigger, right? So what happens when the numerator stays the same and the denominator gets bigger? You get a smaller fraction. So each term is getting smaller and smaller and smaller. In other words, this sequence is trending towards 0. So that's usually what we're concerned about with a sequence. So we're often concerned with the limit of a sequence. That's what we're often concerned with the limit of a sequence. That is a number that the terms approach. And I'll put in parentheses if there is one. Because sometimes, and you'll see what I mean, sometimes the terms don't approach a value. Like in this one. If I kept going, this is going to be negative 5, negative, we can't do simple math, negative 7, and then so on. That's going to keep getting bigger negatively, so that's going to trend towards negative infinity. This one, like I said, is going to trend to 0, because the fraction keeps getting smaller and smaller and smaller, because the denominator keeps getting bigger and bigger. So when we find the limit of a sequence, basically we're just taking the limit of a given sequence and seeing what value it approaches if there is one. And so, if I make another note here, so I'm going to let a sub n, and I'm going to put fancy brackets around. I'm just putting brackets around it, and usually we let this notation define a sequence. So we're letting this be a sequence. All right. Then the limit as n approaches infinity, because the values of n, like the subscript 0, 1, 2, that keeps going on forever. We could go on as long as we want to. Here I just list the first 5 terms, but I could have listed 100 terms if I wanted to, but that's ridiculous. So the limit as n approaches infinity of my sequence will approach L. Right? Where capital L is the limit of the sequence, if it exists. So, this is very similar to, doing limits of functions in Calc 1. It's practically identical. So what we say in this class, however, is if a sequence has a number as a limit, the sequence converges. If a sequence is undefined, plus or minus infinity, the sequence diverges. So, this is what we're usually interested in. We want to see what the limit goes to. If it goes to a number, it converges. If it doesn't, if it's undefined or plus or minus infinity, it diverges. So basically when we're dealing with sequences, we're just seeing, if a sequence, we take the limit of the sequence like we would take the limit of a function in Calc 1. We do it the same way and see if it converges or diverges. That's it. So I'll make another note here. Many of the familiar rules for limits of functions hold for limits of a sequence. So basically all those rules for limits that you learned in Calc 1, they hold for limits of a sequence. And that includes the squeeze theorem, you may have also heard this called the sandwich theorem, but this includes the squeeze theorem, and another useful rule that you've seen in Calc 1 called L'Hopital's rule. To compute limits of a sequence. So basically all I'm saying here is you could take the limit of a sequence the same way you could take the limit of a function. And that includes using all the properties of limits you learned in Calc 1, the squeeze theorem, and L'Hopital's rule. So isn't that pretty sweet? It really is. So yeah. So basically when we're doing this, when we're taking the limits of a sequence, that's all we're really trying to find, if it converges or diverges, using the same values or same properties learned in Calc 1 for the limit of a function. It's pretty much identical. There are some subtle differences. They're not really that common, but you'll see what I mean. Okay. So let me make a note here. So note the limit of a geometric sequence is determined entirely by its ratio which we denote as R. So what do I mean by this? It's okay if you don't know what this means yet. You know what a geometric sequence is. It's a product of a number times the term. What do I mean by ratio? So it's the ratio that it's raised to, and you'll see what I mean. A geometric sequence is going to come up a lot in this chapter, especially when we talk about geometric series. So if I let a times r to the n be a geometric sequence, here's what I have. So you can see how this is geometric, right? Because I have a number times r to the n power. So the ratio r is right here. It's the number that's being raised to by the term in the sequence. This coefficient a, that's what makes it geometric, because I told you a geometric sequence is when you multiply a number by the term. That's what a is doing. All right. So if I have this, then I have the following. If the ratio is greater than 1, then a times r to the n power is going to go to positive infinity. And if I missed a little piece on this. Hold on, I'm going to tack it on here. So if r is greater than 1, this is a sloppy greater than symbol. If r is greater than 1, then a times r n is going to go to positive infinity if the coefficient out front here is positive. Now that makes sense, right? Because, you know, this just means that if r is bigger than 1. So, and if the coefficient is, you know, if it's a positive coefficient, well, a positive number times another positive number is going to be positive, right? And that's if this is positive. That makes sense. Now, we looked at one of those right here already on the first page. This right here, like I said earlier, in this case, r is going to be 2, right? Well, 2 is certainly greater than 1. And so in this case here, right, if I looked at this as a particular case here, that would be, you know, let me just jot it down here for reference. This would be, so 2 to the n is the same thing as saying 1 times 2 to the n, right? So in this case, a would be 1 and r would be 2, right? So if I look here, well, 2 is greater than 1 and a is positive, right? A is 1. So since that's the case, and I told you right here, if I kept listing these terms, right, what's this going to go to? Well, you'll see this, like the next term will be what, 32, 64, and so on. That's going to positive infinity. All right. The next case, so this right here, that would go to positive infinity, right? That's if I had, and that's a particular case of this condition right here. If r is less than my bad. I missed one. Sorry, my bad. Well, I guess it's a good thing I don't have whiteout, huh? I'll put it up here. A sub r to the n will go to negative infinity if a is negative, right? Because I'll have, I'll have a negative number, right? I'll have a negative number times a positive value. That'll make it go to negative infinity. So and that's this case, and then the third case is a times r to the n will go to 0 if a is equal to 0. Well, that's obvious. If 0 times anything is going to go to 0, obviously. So you know, we'll see what what I'm talking about here when we keep getting into series and sequences. But basically, if you have a geometric sequence, the ratio here dictates if it goes to positive infinity, negative infinity, or 0. And you'll see what I mean. You'll see what I mean when we start, you know, looking at particular cases going forward. It's really not that bad. So here's some examples. You know, if r is greater than 1, right? So here's an example. This is actually this example right here. 2, 4, 8, 16. That's going to go to infinity, right? That's a geometric sequence because in this case I have my sequence here is going to be 2 to the n power, where I'm starting at 1 in this case right here, because this is 1, 2 squared, 3, 2 cubed, 2 to the 4th, and so on. That's going to go to infinity. So that's very similar to this one. And you know, if I look at this one, however, that's an equal sign, sorry. If r is equal to 2/3, and my first term is 2/3, my second term is 4/9, 8 over 27, 16 over 81, 32 over 243. It seems like I'm doing something completely random here, but what's this trending towards? So what's happening here? The fraction, I mean, yeah, the top is getting bigger, but the bottom's getting bigger at a bigger rate. So this fraction is actually, you know, it's getting smaller. So this one's trending towards 0. What does this sequence look like? Well, it's actually just 2/3 to the nth power. Where n is greater than or equal 1. So if you don't believe me, just like, all right, 2/3 to the first power is what? 2/3. What's 2/3 squared? Well, 2 squared is 4. 3 squared is 9. What's 2 to the third? 8. What's 3 to the third? 27, and so on. This is 2/3 to the 4th, 2/3 to the 5th, and so on. So this is trending towards 0. All right. And these are geometric sequences, and you'll see what I mean when we start talking about series in the next section. But all right, so let's go on to the next page here. Let's actually look at some other kinds of examples. So determine whether the sequence a sub n equals 2n squared minus 3n plus 1 over 5 minus 7n squared, that's squared, for n is greater than or equal to 1, converges or diverges. If it converges, find the limit. All right, so what did I say earlier? when we're trying to determine whether a sequence converges or diverges, we're just taking the limit, right? If we have a sequence, then we take the limit of the sequence. If it exists, it converges. If it's undefined or plus or minus infinity, it diverges. And we do it by doing all the all the rules we learned from Calc 1. Okay. So take the limit. So the limit as n approaches infinity of this sequence. All right, how do I take the limit of that? So this is, using what you learned in Calc 1 and applying it to to a sequence instead of a function. I mean, they're almost exactly the same thing, but from a different perspective, really. So, if you could look, since we're going to infinity, right, you could look at the largest power here and the largest power here and compare their coefficients, right? So the coefficients of the largest terms in the numerator and denominator is 2 over -7. So you could say, all right, since this is the largest, since this right here is the dominant term in the numerator, and this is the dominant term in the denominator, you could just compare the ratio of their coefficients, which is 2 over -7. So then you could say this goes to 2 over -7. And that's perfectly fine. That's, that's the way you would do it before using L'Hopital's rule in Calc 1. But, and most students like using L'Hopital's rule because it's very efficient and it's very straightforward. It's easy to wrap your mind around. If you take the limit here, obviously you're going to get infinity over here over another infinity. So you could, if you do it this way, this is going to approach infinity over infinity, which is indeterminate form, right? So since it's indeterminate form, it means you could use L'Hopital's rule. So you could do it this way, or you could compare the dominant terms. Either way is fine. It's the same way you learned in Calc 1. So how do we use L'Hopital's rule? Take the derivative of the numerator, the denominator, and then take the limit again. So limit as n approaches infinity. So what's the derivative of the numerator? It's going to be 4n minus 3 all over the derivative here. So that's going to be -14n. Take the limit of that again. So if you take the limit there, all right, well, infinity minus, that's still infinity, over -14 times infinity, that's still infinity. So that's indeterminate, right? That's indeterminate. So you could use L'Hopital, right? L'Hopital's rule again. All right. What's the derivative of the numerator? 4. Derivative of the denominator? -14. Well, that obviously reduces to -2/7, which is exactly what I got here. So, either way, it's fine. But, yeah. So that's what the limit of the sequence is, so that means it converges. All right, so pretty straightforward. It's almost like taking, the limit of a function, but that's the basic idea. Okay. So let's look at a few more examples here. So same instructions here. Just looking at these examples here. Determine whether the sequence a sub n equals -1 to the nth power times n over n squared plus 1 for n greater than or equal to 1 converges or diverges. If it converges, find the limit. So, you know, hopefully you've kind of dusted off your old limit, your limit techniques from Calc 1, because they're going to show up here. Alright, so this is my sequence. So I want to take the limit, right? Alright, I want to take the limit. Okay, well, now I mentioned it on the first page, but you know, you could just go straight. It could be a straightforward limit, but this one's not so straightforward, and it's all because of this little guy right here. I mean, it's staring you in the face. That term right there that's being multiplied by this, that's kind of making you feel a little uncomfortable. So all this means is that this -1 to the nth power, what that means, and I'll jot it down here. That means the terms in the sequence alternate in sign. What do I mean by that? Well, that means depends. So in this case, I'm starting at 1, right? So if I plug 1 in here, right, I have -1 to the first power, and times this stuff with 1 in it. All right. Well, so -1 to the first power. That's, you know, that's going to be -1. So the first term is going to be negative, right? Then I go to the next term. Well, n is equal to 2. All right. Well, -1 squared is going to be negative times a negative, which is a positive. So the next term is going to be positive. And then when I get cubed, I get negative, and then positive, and so on. So what that means is this term right here just means the sequence alternates in sign. And later on in the chapter, when we talk about alternating series, you're going to see that show up a lot. Okay. So since -1 is there, this means the terms alternate in sign. So, you know, this is going to mean that, what's that going to mean ultimately? It means that this term's either going to be negative or it's going to be positive, right? So it's either going to be negative 1, positive 1, negative 1, positive 1, times whatever this number is when you plug in it. Alright, so negative 1 to the n, that's just basically a way of saying it's going to either equal negative 1 or positive 1. Negative 1, positive 1, negative 1, positive, and so on. Alright? So since this equals, it's just depending on which term I'm at, but that's what it means really. So since I have that, now I could say the following. Right? So that means my original sequence is either going to be positive or negative. All right? So if this is positive, right? So what's this positive? Well, it's that, right? So that means this is going to be less than or equal to the positive form of the sequence, and it's going to be greater than or equal to the negative form of the sequence. All right? This is the negative one. So this is the case where it's negative. Right? This right here is the case when this is positive. Right? That's positive 1. That's negative 1. So my original sequence is it's caught between these two terms, just depending on which term I'm at. Okay. So now that I have this, how do I take the limit of this when I have it caught between two things? What am I going to use here? I'm going to use the squeeze theorem. So since this sequence, which is the sequence I was started with, is caught between two things, I could use the squeeze theorem. So now I have this. So now I could try the squeeze theorem. Alright, so how do we use the squeeze theorem? You take the limit of the bounds on the inequality. So now the limit as n approaches infinity of this. Well, what does that equal? Well, that's easy, right? That's an easy limit. The dominant term here is n. The dominant term down here is n squared. So this is going to infinity much faster than the top. So this is going to go to 0, right? And the limit as n approaches infinity of the right one, well, that's the same thing, right? This is going to go to negative, this is basically the same thing. That's going to go to 0 as well. It's just this one's negative. Negative 0 is still 0, obviously. So because these go to 0, what does that mean about this one? This one's caught between two functions that go to 0. So then this one is going to be trapped in between by the squeeze theorem. So this one will have to go to 0 as well. So therefore, by the squeeze theorem, the limit as n approaches infinity of the original sequence, which is the sequence in between, will go to 0. That's it. So does this does this sequence converge or diverge? Well, it converges. There's nothing wrong with 0. There's nothing wrong with that, so it converges. This is very similar to using the squeeze theorem in Calc 1, but the only thing that might be slightly different is this right here. Usually we use the squeeze theorem for things like trig functions, and you're going to see examples like that, and you're actually going to see one right now. Okay. Determine whether the sequence a sub n equals sine of n quantity squared over n converges or diverges. If it converges, find the limit. All right. So the first thing you might try to do is just take this limit, right? All right. So let's try this. The limit as n approaches infinity of sine of n quantity squared over n. Okay. So the first thing you might do is, do this. All right. So sine of infinity. Well, what does that go to? So as n gets bigger, right? Right. So sine of infinity. So sine of, what's sine doing? It's oscillating, right? So, we know what the bottom is doing. N is getting big. So the denominator is infinity. That's easy. But what about the top? Sine of infinity. Sine of infinity is not infinity. I see that mistake a lot, but that's not the case. Sine of n when n is big. So, as you already know, if I graph it in your calculator, and you know this from trigonometry, but sine of x sine of x is caught between -1 and that should be +1. Sine of x is caught between -1 and 1, right? Hold on. Should do small values here. Oop, you know what? I flipped it around. That's what I did. This should be -10 and 10. This is -1 and 1. Yeah, there we go. So that's what, that's what sine does. So it's always caught between -1 and 1. It's never going to go on that. But as n gets bigger, so as n keeps going further to the right, this just keeps oscillating, right? So the numerator here is undefined. The limit, the limit of sine just keeps going forever. It doesn't converge to a specific value. So doing it this way is not going to work. Uh-oh, frown face. So what do? Well, I got to use the squeeze theorem to my advantage. You should definitely try the squeeze theorem if you have sine or cosine in your sequence. That's an important note to make. That's the same thing if it were a function, right? I know I use x here, but it's the same idea. Because sine or cosine, as it gets bigger, they're undefined. But if you use tangent, that's different. Tangent's completely different. So, okay. So let's try to squeeze there. So how am I going to do this, though? Well, what do I know about sine and cosine? So I already alluded to it. sine and cosine are caught between, the range of those functions is between -1 and 1, right? It's always between -1 and 1. So I know that sine of n is less than 1 and greater than -1. Okay. Well, what I could do is now I can use this to my advantage. I know this. This is a property of sine. So I could use this to build to the sequence that I have by doing the same operation on all three sides. I could do that. That's just algebra. So I have sine of n squared, so let me square all three sides. All right. So now I have sine of n squared is less than, well, what's 1 squared? That's obviously 1. Now, what's -1 squared? That's going to be 1. However, what I could do is, if I look here, this is a value squared, right? So a value squared is never going to be negative, right? Something squared is always going to be positive. So what I could do is I could cut this value off at the smallest value I could think of that's not negative. What is that? 0. So this just comes from the fact that, you know, that part comes from the fact that squares can't be negative. That's it. So now that I have that, all right, now what do I do to get to what I have? Divide all three sides by n. So then I have sine of n quantity squared divided by n is less than or equal to 1 over n, and 0 divided by n is still 0. Okay. So now this is what I have. So now that I have this set up the way I had the previous problem set up, right, a 3-part inequality, now I'm set up to use the squeeze theorem. Okay. So now the limit as n approaches infinity. Well, the left side, this bound, obviously the limit of 0 is 0. And the limit as n approaches infinity of this, what does that go to? That's 1 over infinity, which that obviously goes to 0. So since the limits of both endpoints go to 0, the function caught between, so by the squeeze theorem, the limit as n approaches infinity of sine of n squared over n equals 0, which converges. So, yeah, that's it. You know, doing this is, you know, the idea behind it, but yeah, when it comes to using the squeeze theorem, it usually stems from using a 3-part inequality, and you know, sine or cosine is a dead giveaway for squeeze theorem. You might have seen that in Calc 1. Well, you should have seen that in Calc 1. And in the cases when we're dealing with alternating sequences or alternating series, this is also useful for the squeeze theorem when I have an alternating in sine. Okay. Let's go on to a new topic in this section. So note, a sequence increases if terms get bigger from left to right. and it decreases I can't spell. If the terms get smaller from left to right. You know, that's basic common sense. But there's also another very, there's also a very useful technique that you learned in Calc 1, and it involves the first derivative. Well, what do we know about derivatives? They have a lot of interpretations, but one of them is what? You learned this in Calc 1. So how do we know if a function is increasing or decreasing? A function increases or decreases based upon the value of the derivative, right? If the derivative is positive, so if f prime of x is positive, it means the function is increasing. If the f prime is less than 0, or if f prime is negative, that means the function is decreasing. So let me make a little note here. You can treat the terms of a sequence as values of a continuous function, and use the first derivative to determine whether a sequence increases or decreases. So, this seems, it's actually really straightforward. So, let me look at an example right here. I could squeeze it in. Determine whether the sequence a sub n equals n plus 1 over n plus 3 increases, decreases, or neither, or does neither. So just like I said here, what you could do is you could let the sequence represent a continuous function. So I'm going to let f of x be equal to x plus 1 over x plus 3. I'm just letting this sequence be a function now. And then I could take the derivative of this function. And if the derivative is positive, the series increases. If the derivative is negative, it decreases. Which is exactly what you learned from Calc 1 about increasing and decreasing functions. Like when you did concavity and stuff like that. Concavity deals with the second derivative, but I'm getting ahead of myself. Alright, so what's f prime of x equal to? How do you take the derivative of this? Well, use the quotient rule. Alright, low d high minus high d low. Alright, so low is x plus 3. D high, the derivative of x plus 1 is 1, so low d high minus high, which is the quantity x plus 1, times d low, which is 1, all over low squared, which is x plus 3 quantity squared. Now, looking at this, it's hard to see if this is positive or negative. You might have to do a little algebra here. Well, that's not bad. Just, I have x plus 3 minus x plus 1 all over x plus 3 squared. So now if I continue with that, well, I'll distribute the negative here, combine like terms. So I'll have what? So the x's will cancel. I'll have 3 minus 1, which is 2, all over x plus 3 quantity squared. All right. So the derivative of this is this. So this is the first derivative. Is this always positive or negative? And how can I tell that this is always positive or negative? Well, the numerator is 2, right? 2 is positive, right? And the denominator is something squared. I just talked about this a moment ago. Anything squared, right? Right? Anything squared, squares can't be negative. So this right here is always positive. So I have a positive 2. So this is positive. And this is always going to be positive because squares can't be negative. So a positive divided by a positive is always going to be, that's always going to be positive. So since the first derivative is always going to be positive in this case, what can I say? I could say that this sequence increases. So since the first derivative is positive for all x, the sequence increases. That's it. Just take the first derivative and compare and see if it's always going to be positive or if it's going to be negative for all x. Right? If you plug, you're going to get something squared. That's going to be always positive. 2 divided by something positive is always going to be positive, so it's increasing. And that's it. That's it. Okay. So there's a lot of notes in this first section in Chapter 10, but we're kind of making our way through it. So on the next page, you know, sometimes this technique that we just did, where when we take the derivative of a function and see if it's positive or negative on the values of x, sometimes you can't do this depending on the sequence you're given. If you're given a nice sequence, like a nice function, then it's nice. You could do it easily. But you know, sometimes that technique isn't useful. So note, in some cases, it's not possible to use the derivative to determine whether a sequence increases or decreases. So here's another approach. So here's what we're going to do instead. So definition. Let a sub n be a sequence with positive terms and so that part is important. It has to be a positive term sequence. And suppose the limit as n approaches infinity of, now don't get fooled by this notation. This is a sub n plus 1. The whole subscript is n plus 1 all over a sub n equals L. So what does this mean? So a sub n plus 1 means the next term in the sequence. A sub n is the previous term. So this is, you know, if you plug in, for example, if I plug in n equals 1, this is a sub 1, and this is a sub 2. If this is a sub 9, this is a sub 10. This is the next term in the sequence. This is the previous term in the sequence. So if you take the limit of the ratio of two consecutive terms in a sequence, and you get the following, this is what we could say. So if L is less than 1, the terms eventually decrease. And then B, if L is greater than 1, the terms eventually increase. What do I mean by eventually? Well, it means that, you know, you could list off the first 5 terms of a sequence, and it might look like it's decreasing, but by the 10th term, it's actually going to start decreasing. So eventually means, you know, it could start off, like if I were to plot the sequence just for an idea, it means it could start off like this. It could start off doing this, but then eventually it's going to go down like that. So that's what we mean by eventually. It looks like it's increasing, but at some point it's going to start going down. It's kind of like a roller coaster. You're going up, and then eventually you're going to go down. So that's what we mean by eventually. They don't start increasing right off the bat, or decreasing for that matter. So all I'm doing is computing the limit of a consecutive terms in a sequence. If I get something less than 1 or greater than 1, then those are my conclusions. So let's look at an example. Determine whether the sequence a sub n, you're going to love this, 4 to the nth power divided by n factorial increases, decreases, or does neither. All right. Oh, factorial. Oh boy. No one likes that. So what does factorial mean again? Well, you know, I want you to recall something. So factorial means, you know, you take the product of that number all the way down to 1. So if I were to list out the terms of factorial, that's going to be n times the next one that goes less than it. So it's going to be that term times 1 less than that. So that'll be n minus 1. Then 1 less than that, n minus 2, times all the way down to 1. So, you know, you might have forgotten what factorial represents, but so for example, what's 4 factorial? Well, that's 4 times 1 less than 4 is 3, times 1 less than 3 is 2, times 1 all the way down to 1. So 4 times 3 times 2 times 1. So you could just do that in your calculator, but you could do it in your, you know, you could just type that in your calculator, but you could do factorial in your calculator. 4, and I think it's under math. It's under probability, yeah. So if you go to the probability, it's number 4 factorial. Oop, sorry. 4 math, so that's 24. So 4 times 3 is 12, 12 times 2 is 24, times 1 is 24. What's 0 factorial? Interesting. 0, 1. Yeah, 0 factorial is 1. So, just keep that in mind. That's what factorial means. It might have been a while since you've seen that, but all right. So this is my sequence. All right, so if this is what a sub n equals, what does a sub 1 look like? So all you're doing is replacing n with n plus 1. All right, so that's going to equal 4 to the n plus 1 power all over n plus 1 quantity factorial. All right, so now what I'm going to do is I'm going to compute this ratio, the limit of this ratio. So compute the limit as n approaches infinity. Now a sub n plus 1 is going to be in the numerator, so it's going to be this divided by this. This might look a little ugly initially, but we'll worry about that later. So that's the a sub n plus 1 all over a sub n, which is 4 to the n over n factorial. So this right here, that's a sub n plus 1, and this is a sub n. All right, just like this says. So now I got to compute this ratio. All right, well that looks ugly. Well, how do we deal with a complex fraction? We could rewrite that, right? What can I do here? I could bring this up and take the reciprocal and write it as multiplication. So this times the reciprocal of this. So 4 to the n plus 1 over n plus 1 factorial times the reciprocal of this. That'll be n factorial all over 4 to the n. All right. Now, what I'm going to do here is I'm going to collect the like terms together in their own common ratio. You don't have to do that, but it just makes it look a little better. So I'm going to write the 4 to the n terms together in one fraction times the factorial terms as another fraction. Okay, so now what I got to do here is I got to figure out what this goes to. So let me just rewrite it down here. So let's look at each fraction separately. So what does this go to? What does that go to? All right, so you could just use properties of exponents, right? Properties of exponents, this is 4 to the n plus 1 over 4 to the n. So that's going to be what? 4 to the n plus 1 minus n power, right? Using properties of exponents. So that gives you what? 4 to what power? The n's cancel. So I just have 4 to the first power, which is 4. All right. Just using algebra, right? So this becomes 4. All right, well that's easy. Now, the factorial part, that looks a little trickier. But if you use the definition of factorial, it's really not that bad. So instead of just writing this, I'm going to write it out as the definition of factorial. So if I write out the terms of n factorial, right? So if I write out the terms of n factorial, right? So I start at n, right? Times, what's the next term I could write? N minus 1, right? And I could keep going, but eventually I'm going to go all the way down to dot, dot, dot. So that's going to be times 2, then times 1, right? That's where it stops. So this is just term by term of what factorial means. Now let me do that for this one down here. Let me list this one out term by term. So this is going to be what? What's the first term? n plus 1. All right, and that's going to be multiplied by the next lowest one. So if I take 1 away from that, that's going to be n, right? And if I take 1 away from that, that's going to be n minus 1 times all the way down to 2 and then 1. Now I want you to see something here. This is where the magic happens. So this right here, the numerator listed out term by term is all of this, right? The denominator listed out term by term is all of this. What do they have in common? So if you look here, well, isn't this, are all these terms in here? All of these terms right here? So if you look here, right, all of these terms are right here, right? Everybody see that? Yeah. So what happens is if I lift these out term by term, these terms are going to cancel out with these terms down here. And all I'm going to be left with is a 1 over n plus 1 term. So the only term that survives is the n plus 1 in the denominator. That's it. So this term, this n is going to cancel out with this n down here. This n minus 1 is going to cancel out with that one. And all these in here are going to cancel out with those in there. The 2's cancel and the 1's cancel. So all I'm left with is 1 over n plus 1. So that's what this goes to. So this, when it's all said and done, is going to go to 1 over n plus 1. And that's because of what I have here. I know that seems a little tricky, but that's the basic idea of how you get factorials to reduce. Just list out all the terms of each one. So it looks a little harder than it really is, but so when it's all said and done, I end up with the limit as n approaches infinity of this goes to 4 times, and what this reduced to? Well, all of these canceled out, so I just have 1 over, and everything down here canceled out except for n plus 1. So now what's the limit of this? Well, 1 over infinity, that goes to what? That goes to 0. So this is just, the limit as n approaches infinity of 4 over n plus 1 equals 0. Okay. So, all right, what's our conclusion then? 0. Our limit is 0, right? So is 0 less than 1 or greater than 1? Well, obviously it's less than 1, so the terms eventually decrease. So since the limit equals 0, which is less than 1, the sequence eventually does what? Well, less than 1, so it eventually decreases. Ta-da! Okay. You know, this is the trickiest part here, but as long as you look at the term by terms and see how they cancel out with the common terms, it's really not that bad. So that's what this whole thing, the whole thing goes to n plus 1. All right, I know that these notes seem pretty long, and we're almost done with this first section, but I just need to talk about one more thing. I just need to talk about one more thing in this section, and then we're done. So definition. So the last thing I want to talk about in this section is if a sequence is bounded. And it's pretty straightforward. So a sequence A sub n is bounded if there is a number capital M, which we denote as capital N, such that the entire sequence is caught below M for all the terms in the sequence. So graphically, this just means that the sequence is caught between the value of M. So this is, graphically speaking, right? This is N, this is A sub N. So if I plotted the terms of a given sequence, right? Let's say when I plotted the terms of a given sequence, it looks like the following. This is a random array of numbers. But let's say that's what my sequence looks like. Right? This is the first term, second term, and so on, right? This just means that, let's say I do one more term. It's bounded if all the terms in the sequence are caught between two values of n. So that just means it's caught between that value and the opposite of that value. That's why there's an absolute value symbol here, because it's caught between m and negative n. This means it's bounded. So all the terms in the sequence are caught between those two values for m. That's all it means. So bounded sequences are caught between negative m and positive m. That's it. That's what we mean by bounded. But if you want to show that a sequence is bounded, all you have to do is show that there's a value that it's caught between. That's really it. And it's really straightforward. Example. Show that the sequence A sub n equals 5 plus 2 sine of n is bounded. Alright, well, this is 5 again. So, alright, what do we know about sine? So basically all I'm doing is I'm trying to show you that this value is, this whole sequence is caught between some number. It's never going to go above it or below it. So it's caught between two values. So what do we know about sine? I know that sine is what? We did this already. Sine is always between 1 and negative 1. Alright, so now if I just use this to build to what I have and go from there. So let's multiply it by 2. So when I multiply both sides by 2, well, that's going to be 2, and negative 1 times 2 is negative 2. And then if I add 5 to it, right? So if I add 5 to this side, I get 7. And if I add 5 to negative 2, I get 3. Alright, so this is my sequence, right? So based upon this, what do I know? So the sequence is caught between two values, 3 and 7. It's caught between two values, 3 and 7. So it's never going to go beyond those two values, so I could say that the sequence is bounded. So because of this, I could say, I could say the following. I could extend this to be the same value and say this is -7 if I wanted to. Since a sub n, 5 plus 2 times sine of n, is stuck between 3 and 7, the sequence is bounded. And that's really it. There is another way that you can show that a sequence is bounded, and it's very, it's very straightforward. Definition, or I could say note. Another way to show a sequence is bounded is if the terms of a sequence approach a finite limit. So that's basically the same thing as saying the limit of a sequence exists. It's the same thing as that, which, that's easy. If the limit exists, then we could say it's bounded. And that's easy. So prove that a sub n equals 4n squared over 8n squared plus 3 is bounded. That's easy. Take the limit. Now you could take this limit, one of two ways. You could compare the coefficients of the dominant terms, or you could use L'Hopital's rule. This one's easy. This is the dominant term because it's squared, and well, it's the only term up there. And this is the dominant term because it's squared. To compare those coefficients, it goes to 4 over 8, which is a half. That's a finite limit, duh. So, therefore, the sequence is bounded. Ta-da! Alright, so when it comes to sequences, that's mostly what we're interested in this section. It's, getting familiar with what a sequence is, how we use sequences, etc. So going forward, so that's it for 10.1, which, it was a long section, I'm not going to lie. There's a lot to it. So yeah, there was a lot of notes for that section. But so what we're going to do going forward in 10.2 and so on is in 10.2 we're going to look at series, and then going beyond that we're going to look at convergence tests for series and how to determine if a series converges or diverges. So those are the notes for 10.1. Whew, that was a long one. So yep, that's 10.1. That's the end of the video.